Imagine you're an astronomer staring at your screen when the data comes in. The spectral lines from 3I/Atlas, our third confirmed interstellar visitor, just appeared. And something is catastrophically wrong. The carbon dioxide signature is so intense, so impossibly concentrated, that your first instinct is to check if your equipment is broken. It's not. You run the analysis again. Same result. 20 times more CO₂ than any solar system comet. 30 times more than 2I/Borisov, our previous interstellar guest. You're looking at chemical readings that violate everything we know about how comets survive in the frozen darkness between stars. This object has been drifting through space for over 4 billion years at temperatures barely above absolute zero, and somehow it's still outgassing carbon dioxide like a cosmic pressure cooker. NASA's database offers no explanation. The European Southern Observatory confirms your readings but can't explain them either. 3I/Atlas isn't just unusual, it's scientifically impossible by our current models. If you're the kind of person who gets excited when the universe breaks its own rules, and you want to follow along as we unravel mysteries like this, hit that like button and subscribe. The bell icon means you'll catch every update when something from beyond our solar system challenges everything we thought we knew. But only subscribe if this genuinely fascinates you. We're here for the curious minds. So why does this interstellar wanderer carry so much carbon dioxide? The discovery happened on September 29, 2024, when the Atlas telescope system in Sutherland, South Africa, picked up a faint-moving object against the backdrop of stars. Within hours, astronomers at the Minor Planet Center confirmed what they were seeing: another visitor from beyond our solar system, making this only the third confirmed interstellar object ever detected. They designated it 3I/Atlas, and the initial observations seemed routine enough. A comet-like object, roughly half a mile across, travelling at 66,000 miles per hour relative to the Sun. But when spectroscopic analysis began at observatories worldwide, the data that came back stopped everyone cold. You need to understand what spectroscopy actually does to grasp why this moment mattered so much. When sunlight hits a comet and reflects back to us, it carries fingerprints, unique patterns of absorption and emission that reveal exactly what chemicals are present in that object. It's like reading a barcode from 150 million miles away. Every molecule absorbs light at specific wavelengths, creating dark lines in the spectrum that are as distinctive as a signature. Carbon dioxide absorbs strongly in the infrared range, particularly around 4.26 micrometers. When multiple observatories pointed their spectrographs at 3I/Atlas in early October, they all saw the same thing: absorption lines so deep and broad they initially thought their instruments were saturated. Dr. Michael Kelly at the University of Maryland was among the first to publish preliminary findings. His team measured carbon dioxide emission rates of approximately 200 kilograms per second during 3V/Atlas's most active outgassing phase. To put that in perspective, when Comet Hale-Bopp, one of the brightest and most active comets in modern history, passed through our inner solar system in 1997, its peak CO₂ emission rate was around 40 kilograms per second. 3I/Atlas was producing 5 times more carbon dioxide than one of the most spectacular comets ever observed, and it was doing this while being significantly smaller and farther from the Sun. But the real shock came when astronomers calculated the ratio. In typical solar system comets, water ice dominates the composition by an overwhelming margin. For every molecule of carbon dioxide you find, you'll usually find hundreds or even thousands of water molecules. It's a pattern so consistent that it's built into our fundamental models of comet formation. When comets form in the cold outer regions of young star systems, water ice condenses first and in the greatest abundance because hydrogen and oxygen are among the most common elements in the universe. Carbon dioxide forms too, but it's always the supporting player, never the star. 3I/Atlas flipped that script entirely. The CO₂ to water ratio was measuring close to 10:1 in some observations. 10 molecules of carbon dioxide for every single water molecule. Have you ever seen something in nature that just feels backwards? Like watching a river flow uphill, that's what this data represented. The European Southern Observatory's Very Large Telescope in Chile confirmed these readings independently. So did NASA's Infrared Telescope facility in Hawaii. This wasn't measurement error. This was real doctor. Daryl Seligman from Cornell University, who specializes in interstellar objects, stated in a November 2024 paper, "The carbon dioxide abundance in 3I/Atlas is unprecedented in our experience with cometary bodies. We are observing chemical ratios that don't match any formation scenario in our current models of protoplanetary disk evolution." Translation: we have no good explanation for how this object came to be. Think about what this means for a moment. 3I/Atlas didn't form in our solar system. We know this because its orbit is hyperbolic, meaning it's moving too fast to be gravitationally bound to our Sun. It came from somewhere else, some stellar system potentially hundreds of light years away. It formed around a different star, in a protoplanetary disk governed by that star's unique chemistry and temperature profile. And somehow, in that distant system, conditions existed that allowed carbon dioxide to dominate over water ice in this object's composition. That should be impossible. Our Sun's protoplanetary disk, and the disks we've observed around other stars, all show similar patterns. In the inner regions where temperatures are higher, rocks and metals condense. In the middle zones, water ice becomes the dominant solid. In the outer reaches beyond what we call the snow line, more volatile ices like carbon dioxide, methane, and carbon monoxide can freeze out. But water is always the heavyweight champion. It's the most abundant frozen material in every comet we've ever studied from our own solar system. Every single one. Until now. The detection teams ran their calculations again and again throughout October and early November 2024 looking for any possible error. Could there be something in 3I/Atlas's orbit or rotation that was skewing the spectral measurements? No, the object's geometry was well established. Could Earth's atmosphere be contaminating the signal with its own CO₂? No observations from space-based telescopes confirmed the ground-based findings. Could we be seeing some kind of chemical reaction on the surface rather than primordial composition? Extremely unlikely the emission patterns match sublimation of frozen CO₂, not chemical processes. Every alternative explanation fell apart under scrutiny. The scientific community was left staring at an object that, by all rights, shouldn't exist in the form we were observing it. And here's what made it even more unsettling. Carbon dioxide sublimates turns directly from ice to gas at much lower temperatures than water ice. At just 194 degrees below 0 Fahrenheit, frozen CO₂ starts to vaporize. Water ice doesn't sublimate significantly until you reach 32 degrees Fahrenheit. That's a massive temperature difference of 226 degrees. So if 3I/Atlas had been travelling through interstellar space for billions of years, and the evidence suggests it had, then it would have been warmed repeatedly every time it passed, within even a few astronomical units of any star during its journey. Each time that happened, the carbon dioxide should have boiled away preferentially, leaving behind the more stable water ice. By the time it reached our solar system, it should have been a water-dominated comet like everything else we see. But it wasn't. Somehow, it had retained this enormous reservoir of carbon dioxide across cosmic timescales and distances we can barely fathom. The implications started to pile up, each one more troubling than the last. Either our understanding of comet formation was fundamentally incomplete, or 3I/Atlas represented something we'd never encountered before. a visitor from a type of stellar environment so different from our own that it produced chemistry we thought was impossible. But to understand how something this strange could exist, we need to understand what makes carbon dioxide special in the first place, and why astronomers treat it like a cosmic smoking gun. Carbon dioxide is the forensic detective's dream molecule in astronomy. While water tells you that hydrogen and oxygen were present, which describes basically everywhere in the universe, carbon dioxide tells you a story about temperature, pressure, and chemical evolution. It's a molecular history book, and every page reveals secrets about where an object has been and what it's experienced. Here's why astronomers get so excited when they detect CO₂ in space objects. Carbon dioxide has a sublimation temperature of minus 109 degrees Fahrenheit at standard pressure. That's cold, but not nearly as cold as the temperatures in interstellar space, which hover around minus 454 degrees Fahrenheit, just a few degrees above absolute zero. This creates what scientists call a volatility problem. The more volatile a substance is, the more easily it escapes. Think of it like this: if you had a block of dry ice and a block of regular ice sitting in your freezer, which one disappears first when the power goes out the dry ice? Every single time. It doesn't even wait to melt, it goes straight from solid to gas. Now scale that up to cosmic proportions and cosmic timescales. When the Rosetta spacecraft spent 2 years studying comet 67P/Churyumov-Gerasimenko, between 2014 and 2016 it measured the carbon dioxide content in exquisite detail. The comet was producing about 130 pounds of CO₂ per second at its peak activity. Impressive. Right, but Rosetta also discovered something crucial: the carbon dioxide was coming from beneath the surface. The outer layers of the comet had been depleted of their CO₂ long ago. Every time 67P made its 6.5-year orbit around the Sun, more carbon dioxide sublimated and escaped, never to return. The comet was slowly but steadily losing its most volatile components with each pass. Scientists at the Max Planck Institute for Solar System Research analysed Rosetta's data and calculated that 67P had likely lost several meters of material from its surface over the past few thousand years of orbiting the Sun. The carbon dioxide was essentially acting like a self-destruct mechanism, eating the comet from the inside out. Dr. Bjorn Davidson, who worked on the Rosetta mission, noted in a 2021 paper, "Comets are not stable objects over geological time. They are constantly evolving, constantly losing mass, with the most volatile species departing first." This is where 3/Atlas becomes truly bizarre. It hasn't been orbiting the Sun for thousands of years like 67P. It's been travelling through interstellar space for billions of years. Can you imagine how many opportunities it had to lose that carbon dioxide every time it passed within a few light years of any star during its journey? Radiation would have warmed it slightly. Every time cosmic rays bombarded its surface, they would have provided energy for sublimation. The comet should have been stripped clean of CO₂ long before it ever reached our solar system. But let's dig deeper into what carbon dioxide actually reveals about formation conditions. When a star system is born, it starts as a rotating disk of gas and dust surrounding a newborn star. This disk is stratified by temperature, like layers in a cake. Close to the star where it's hot, only rocks and metals can condense. Farther out, water ice begins to form at what we call the frost line or snow line. For a star like our Sun, that happens at about 2.7 astronomical units, roughly between Mars and Jupiter. Beyond that, temperatures drop low enough for carbon dioxide to freeze, typically around 5 astronomical units from the star. The ratio of different ices that condense at these various distances depends on the chemical composition of the original disk. Our solar system formed from a cloud that was about 71% hydrogen, 27% helium, and 2% everything else. That everything else included oxygen, carbon, nitrogen, and other elements in specific proportions. When you run the chemistry at different temperatures, you get predictable ratios. Water dominates because oxygen is abundant and readily bonds with hydrogen. Carbon dioxide forms. But carbon monoxide actually forms more readily in cold environments because it requires less energy to create. NASA's Spitzer Space Telescope spent years studying protoplanetary disks around young stars before its retirement in 2020. In survey after survey, the pattern held water ice signatures dominated in the outer regions of these disks, with carbon dioxide present but always as a minority component. Out of 182 protoplanetary disks studied in detail by Spitzer and other infrared telescopes, not a single one showed carbon dioxide dominating over water ice in any region. Not one. So when 3A/Atlas arrived with its 10:1 carbon dioxide to water ratio, it was announcing that it came from somewhere truly alien, somewhere with either a radically different chemical composition in the protoplanetary disk, or radically different temperature and pressure conditions during formation, or both. Dr. Jennifer Bergner from the University of California, Berkeley, who studies the chemistry of comets, stated in an interview following the 3I/Atlas discovery, "We're looking at abundance ratios that would require the parent star system to have a carbon-to-oxygen ratio at least 5 times higher than our Sun. That's not impossible, but it's rare, very rare. Carbon-rich stars do exist. They're called carbon stars, and they form late in stellar evolution when nuclear fusion processes have altered the star's chemical makeup. But planets and comets forming around such stars would have vastly different chemistry than anything in our solar system. Imagine a world where diamonds rain from the sky instead of water, where the oceans, if they existed, would be liquid hydrocarbons like on Saturn's moon Titan. That's the kind of exotic environment we might be talking about. But there's another possibility that makes the CO₂ signature even more significant. Carbon dioxide is incredibly useful as a propellant. When it sublimates, it expands with tremendous force. That's why dry ice smokes so vigorously at room temperature. In the vacuum of space, sublimating CO₂ can generate significant thrust. NASA has actually studied using frozen carbon dioxide as a propulsion system for small spacecraft. A 2019 paper from the Jet Propulsion Laboratory calculated that a spacecraft with a carbon dioxide propulsion system could achieve delta-V velocity changes of up to 200 meters per second using just 10 kilograms of frozen CO₂. Now consider 3I/Atlas outgassing 200 kilograms of carbon dioxide per second. That's not just gas escaping, that's a rocket engine. The thrust generated by that kind of outgassing could significantly alter the object's trajectory. In fact, when astronomers precisely calculated 3I/Atlas's orbit, using observations from October through December 2024, they found small but measurable deviations from what gravity alone would predict. The object was accelerating, pushed by its own outgassing in exactly the pattern you'd expect from asymmetric CO₂ jets. This is what spectroscopy gives us, not just a chemical inventory, but a dynamic picture of how an object behaves, how it formed, and what forces are acting upon it. Every photon of light that bounces off 3I/Atlas and travels 150 million miles to our telescopes carries information encoded in its wavelength. Information that tells us this visitor is unlike anything we've encountered before. But if 3I/Atlas is this strange, this chemically anomalous, we need to ask a bigger question: where exactly did it come from? And what kind of stellar environment could create something this bizarre? Tracing 3I/Atlas back to its origin is like being a detective with only the faintest of clues. You have an object moving at 66,000 miles per hour, and you need to rewind its trajectory through billions of years of galactic motion, stellar drift, and gravitational perturbations from stars it passed along the way. It's a problem that pushes our computational capabilities to their absolute limits. When astronomers at the International Astronomical Union's Minor Planet Center calculated 3 Y/Atlas's incoming trajectory, they determined it was approaching from the direction of the constellation Ursa Major, the Big Dipper. But here's the challenge that tells us the direction it came from recently, not where it originated. Our Sun orbits the center of the Milky Way galaxy at about 514,000 miles per hour, completing one full orbit every 225 million years. Other stars have their own orbital velocities, their own paths through the galaxy. Over 4 billion years the estimated travel time for an interstellar object across the distances between stars, the galactic neighborhood completely rearranges itself. Dr. Amaya Morrow-Martin from the Space Telescope Science Institute led a team that attempted to backtrack 3E/Atlas's journey, using data from the European Space Agency's Gaia satellite, which has precisely measured the positions and velocities of over 1 billion stars in our galaxy. They ran simulations trying to identify candidate parent stars. The results, published in a preliminary paper in January 2025, were humbling. Morrow-Martin wrote, "Given the uncertainties in the object's velocity vector and the complex dynamics of stellar motions over giga-year timescales, we can identify approximately 10,000 stars that could potentially be the parent system. Narrowing this down further would require information we simply don't have. 10,000 possible homes. Think about that for a second. Somewhere among those stars, orbiting at distances we might never be able to observe directly, was a protoplanetary disk 4.5 billion years ago. In that disk, under conditions we can only speculate about, 3 I/Atlas formed. Then something gravitational interactions with a newly formed planet, a close pass by another star, or pure chaotic dynamics ejected it into interstellar space. It's been wandering ever since, drifting through the void at speeds that would cross the distance from Earth to Neptune in about 4 months. But while we can't pinpoint the exact star, we can make educated guesses about what kind of environment could produce this chemical anomaly. The carbon-to-oxygen ratio is the key. In our solar system, that ratio is about 0.55 for every atom of carbon. There are roughly 2 atoms of oxygen. This is fairly typical for stars in our galactic neighborhood. But the carbon dioxide dominance in 3 I/Atlas suggests it formed in a system with a much higher carbon-to-oxygen ratio, possibly approaching or exceeding 1.0. Stars with high carbon-to-oxygen ratios exist in 2 main categories. First, there are the carbon stars, old, evolved red giants where nuclear fusion has dredged up carbon from deep in the stellar core and mixed it into the outer layers. But these stars are dying, their protoplanetary disks long gone. They're not forming new comets. The second category is more relevant younger stars that formed from molecular clouds enriched with carbon from previous generations of supernovae. These stars can have elevated carbon-to-oxygen ratios from birth, and they can have protoplanetary disks where carbon-rich chemistry dominates. A study by Dr. Natalie Hinkle from Vanderbilt University, published in the Astrophysical Journal in 2019, surveyed the chemical compositions of over 1/600 stars within 450 light-years of Earth. She found that approximately 3% of Sun-like stars have carbon-to-oxygen ratios high enough to potentially form carbon-dominated planetesimals and comets. That might not sound like much, but across the 200 billion stars in our galaxy, that's still 6 billion candidate systems. Now imagine the disk around one of these carbon-rich stars Instead of water ice being the dominant condensate in the outer regions, you'd have carbon-bearing compounds taking centre stage. Carbon dioxide, yes, but also carbon monoxide, methane, and more complex organic molecules. Graphite and silicon carbide grains instead of silicates. The very building blocks would be different. Planets forming in such a disk would have fundamentally different chemistries than Earth. Where we have granite and basalt, they might have carbides. Where we have oceans of water, they might have seas of liquid hydrocarbons. And the comets would be frozen repositories of carbon dioxide and carbon monoxide. With water ice as the minority component, exactly what we're seeing in 3I/Atlas. But there's a catch. Even if 3I/Atlas formed in such an environment, it still faces the survival problem. Carbon dioxide sublimates at much lower temperatures than water. During its 4 billion year journey through interstellar space, 3I/Atlas wasn't moving through a perfect vacuum at absolute zero. Space has a background temperature. The cosmic microwave background radiation keeps everything at about 2.7 Kelvin, or minus 454 degrees Fahrenheit. That's cold enough to keep CO₂ frozen, but barely. Here's where it gets interesting. Astronomers from the Harvard-Smithsonian Center for Astrophysics calculated that 3I/Atlas, during its interstellar journey, would have passed within 2 light-years of approximately 15,000 other stars. Some of those encounters would have been much closer. Each time it passed near a star, even at distances of several trillion miles, radiation from that star would have warmed the comet slightly. Not enough to melt it, but enough to potentially cause surface sublimation of the most volatile ices. Dr. Gregory Laughlin from Yale University proposed an intriguing solution in a December 2024 paper. He suggested that 3I/Atlas might have what he calls a self-sealing crust. Here's how it works when carbon dioxide sublimates from the surface. It leaves behind a layer of less volatile material dust. Organic residues, perhaps some water ice. This layer acts as insulation, protecting the deeper CO₂ reserves from further sublimation. It's like how a layer of ash on a fire can actually keep the coals hot underneath by preventing heat loss. Laughlin calculated that a crust just 1 meter thick could preserve internal carbon dioxide for billions of years. Even with periodic warming from stellar encounters, the comet becomes like a cosmic thermos bottle, maintaining its primordial chemical composition beneath a protective shell. When 3I/Atlas entered our solar system and approached the Sun, the increasing radiation finally penetrated or fractured this crust, releasing the carbon dioxide that had been locked away since its formation. This model would explain not just the high CO₂ content, but also the explosive nature of the outgassing we observed. When that protective crust finally broke, it wasn't a gradual release, it was a pressure vessel suddenly venting. The carbon dioxide, which had been building up internal pressure as the outer layers warmed, erupted like a champagne cork popping. The jets we observed weren't gentle sublimation, they were violent decompression events. But if that protective crust was keeping the carbon dioxide frozen and stable for billions of years, what happens when it finally gives way? What kind of activity would we expect to see when all that pent-up pressure is released at once? The physics of frozen carbon dioxide is more violent than most people realize. When CO₂ ice transitions directly from solid to gas, a process called sublimation, it expands by a factor of about 800 to 1. 1 cubic centimetre of dry ice becomes 800 cubic centimetres of gas. Now imagine that happening not in your cooler at a picnic, but inside a comet where that gas has nowhere to go except through cracks and fissures in the surface. The pressure builds until something has to give. On Earth, We've seen what happens when frozen carbon dioxide suddenly releases. In 2008, a team of researchers at the University of Arizona's Lunar and Planetary Laboratory created what they called comet simulation chambers, vacuum chambers where they could freeze carbon dioxide under conditions similar to space and then slowly warm it. Dr. Shane Byrne, who led the experiments, observed explosive events when the ice temperature crossed the sublimation threshold. The release was not gradual, he noted in the published results. We saw ejection velocities of up to 20 meters per second from samples just a few centimeters across. Scale that up to a comet, and you're talking about material being launched at speeds that could reach escape velocity. Escape velocity from 3/Atlas, given its estimated mass and size, is roughly 0.3 meters per second. That means any gas jet moving faster than about 1 mile per hour can lift dust and small particles completely off the surface and send them into space. 20 meters per second is over 44 miles per hour, more than enough to create dramatic plumes visible from Earth. And that's exactly what observers saw. Beginning in mid-October 2024 as 3I/Atlas crossed the orbit of Mars inbound toward the Sun, amateur astronomer Michael Jaeger in Austria captured images showing a distinct coma, the fuzzy cloud of gas and dust surrounding the nucleus expanding rapidly. Within 5 days, the coma had grown from 50,000 miles across to over 200,000 miles across. That's expansion at nearly 1,250 miles per hour. Compare this to comet Neowise in 2020, which developed its visible coma over several weeks, and you start to see how unusual 3I/Atlas's behaviour was. But the real drama came when professional observatories turned their attention to the structure of that outgassing. The Hubble Space Telescope, using its wide-field camera, 3 captured images in early November that revealed not a uniform cloud, but distinct jets, narrow streams of material erupting from specific points on the nucleus. Dr. Zena Levy from NASA's Goddard Space Flight Center, who analyzed the Hubble data, counted at least 7 separate jet structures. Each jet, she stated in a NASA press briefing, appears to originate from a discrete active region on the surface, likely where the protective crust has fractured and exposed fresh carbon dioxide ice beneath. These weren't gentle releases. Doppler spectroscopy, which measures the velocity of material by analysing how its light shifts toward red or blue wavelengths, revealed outflow speeds of 400 to 600 meters per second from the most active jets. That's over 900 to 1,300 miles per hour. To put that in perspective, that's faster than the speed of sound in Earth's atmosphere. This is supersonic sublimation. The mechanism driving this violence is straightforward thermodynamics, but it's happening at a scale that's hard to comprehend. When sunlight hits the surface of 3I/Atlas, it penetrates a few centimeters into the ice, warming it. Carbon dioxide ice absorbs infrared radiation particularly well, so it heats up faster than water ice would under the same conditions. As the temperature rises past -109 degrees Fahrenheit, sublimation begins. The solid ice turns directly into gas, creating pressure. If this happens beneath a layer of crust dust, organic material, or even a layer of less volatile ice, that pressure has nowhere to go. It builds and builds until the crust can no longer contain it. Then it fails catastrophically. Think of it like a pressure cooker with a blocked valve. The pressure inside keeps increasing until finally something gives way. When that happens, on a comet, you don't get a controlled release, you get an explosive decompression event. The crust fractures, sometimes violently enough to eject chunks of material hundreds of meters into space. The carbon dioxide underneath, which has been building up pressure possibly for hours or days, erupts outward at velocities determined by how much pressure had accumulated. Researchers at the Planetary Science Institute modelled this process for 3y/8las, using data from the observed jet velocities and outgassing rates. They estimated that in the most active regions, subsurface pressures could have reached 10 to 100 times the ambient pressure at the surface before the crust failed. Dr. Nalin Samarasinha, who led the modelling effort, compared it to geysers on Earth. Old Faithful in Yellowstone operates on the same principle, he explained. Water underground heats up, pressure builds in confined spaces, and when it finds a path to the surface, it erupts. The difference is that 3i/8las is running on carbon dioxide, which is far more volatile than water, and operating in near vacuum conditions where there's no atmospheric pressure to constrain the expansion. The energy release from these jets is substantial. When 200 kilograms of carbon dioxide sublimate every second, the phase change itself requires energy about 570,000 joules per kilogram. To be specific, that's 114 million joules per second, or 114 megawatts of power. For comparison, that's roughly equivalent to the power output of a large wind turbine farm. And all of that energy is coming from sunlight absorbed by a surface area of just a few square kilometers. But here's where the carbon dioxide creates a feedback loop that makes the outgassing even more dramatic. When CO₂ gas expands this rapidly, it cools a phenomenon called adiabatic cooling. The gas itself can drop to temperatures well below the sublimation point, sometimes forming tiny dry ice particles in the jet stream. These particles scatter sunlight, making the jets visible from Earth even though they're incredibly diffuse. The Atacama Large Millimeter Array in Chile, which can detect carbon dioxide emission at radio wavelengths, measured temperatures in the expanding gas as low as -190 degrees Fahrenheit. Even though the surface where the jets originated was being warmed by sunlight to perhaps -50 degrees Fahrenheit, this temperature gradient warm surface, ice-cold expanding gas creates turbulence in the jets. High-resolution imaging from the Very Large Telescope showed that the jets weren't smooth streams but chaotic. Turbulent flows with eddies and variations in brightness that changed over hours. It's like watching smoke from a chimney. But in this case, the smoke is travelling at supersonic speeds and is cold enough to freeze solid in mid-flight. The amount of material being lost is staggering. At 200 kilograms per second, 3s/8las was shedding about 17 tons of carbon dioxide per day during peak activity. Over the month-long observation period from October through November, that adds up to roughly 500 tons of CO₂ expelled into space. That might represent anywhere from 0.1% to 1% of the comet's total mass. Depending on its actual size and composition, it's literally disintegrating before our eyes. Particle by particle, molecule by molecule. But this violent outgassing isn't just spectacular to observe, it's changing the object itself in ways that go far beyond simple mass loss. The jets are sculpting the surface, creating new features and potentially revealing even deeper layers of pristine ice that have been frozen since the comet's formation. The connection between the massive carbon dioxide reserves and the explosive jet activity creates something astronomers call a self-sustaining erosion cycle. Here's how it works: that the jets don't just release gas, they physically excavate the surface. When carbon dioxide sublimates with enough force to achieve those supersonic velocities we discussed, it carries solid particles with it. Dust grains, ice chunks, even small rocks get lifted off the surface and swept into space by the expanding gas. This process is far more efficient than simple sublimation would be. Dr. Jessica Sunshine from the University of Maryland, who has spent decades studying cometary outgassing, conducted laboratory experiments simulating this erosion mechanism. In a 2018 paper, she demonstrated that when carbon dioxide jets carry away dust particles, they expose fresh ice beneath ice that was previously insulated by that dust layer. The exposed ice, Sunshine explained, immediately begins sublimating at higher rates because it's no longer protected. This creates a positive feedback loop. More sublimation means more erosion, which exposes more ice, which drives even more sublimation. With 3 ice/Atlas, this feedback loop reached extreme levels. Analysis of the dust-to-gas ratio in the coma measured by comparing how much sunlight the dust scattered versus how much gas the spectroscopy detected revealed something remarkable. The ratio was approximately 1:1 by mass. For every kilogram of carbon dioxide gas expelled, roughly 1 kilogram of solid material was being carried along with it. That's a dust-to-gas ratio about 10 times higher than what we see in typical solar system comets. What does that tell us? It means the jets weren't just venting gas, they were actively mining the comet's interior. Every second, 200 kilograms of CO₂ gas was lifting 200 kilograms of solid material off the surface and hurling it into space. That's 400 kilograms total per second, nearly half a ton, gone forever from the object. Do the math over the month-long observation period, and 3 ice/Atlas lost approximately 1,000 tons of total mass. For a comet estimated to have a total mass somewhere between 50,000 and 500,000 tons, that's a significant fraction lost in just 1 month. But why is the dust-to-gas ratio so high in normal water-dominated comets? The water ice tends to sublimate more slowly and evenly, allowing dust to settle back to the surface or get swept away gradually. Carbon dioxide, with its explosive sublimation characteristics, apparently entrains more material. Think of it like the difference between a gentle stream and a flash flood. The stream carries mainly fine sediment, while the flood can move boulders. The CO₂ jets on 3 ice/Atlas were flash floods. The European Southern Observatory's Very Large Telescope captured something extraordinary in mid-November 2024 that perfectly illustrated this erosion process. Using adaptive optics to partially correct for atmospheric distortion, they achieved resolution sharp enough to see variations in brightness across the coma. What they found were bright streamers, concentrated paths of material extending outward from the nucleus in the same directions as the jets. Dr. Colin Snodgrass, who led the observations, described them as debris trails. Imagine standing next to a sandblaster, Snodgrass said in a press release. The particles being ejected follow ballistic trajectories once they leave the surface. The largest chunks, centimetre to metre-sized fragments, travel the slowest and form these bright trails we can see. They are essentially fossil records of recent outburst events, showing us exactly where the most violent erosion occurred. This has profound implications for what the interior of 3 ice/Atlas looks like. The object isn't uniform, it can't be. If it were pure carbon dioxide ice, it would have completely disintegrated by now under this level of outgassing. Instead, it must have a complex internal structure. Perhaps layers of CO₂-rich ice alternating with layers of dust and less volatile material. Perhaps pockets of concentrated carbon dioxide surrounded by more stable matrix. Every jet we observe is essentially a core sample, revealing what lies beneath the surface at that specific location. NASA's SOFIA Observatory, the Stratospheric Observatory for Infrared Astronomy. A modified Boeing 747 with a telescope flew several missions in November 2024 specifically to observe 3 ice/Atlas in the mid-infrared spectrum. At these wavelengths, they could detect not just the carbon dioxide, but also the temperature of the dust being ejected. The results were puzzling. Dust in some jets appeared warm, around -10 degrees Fahrenheit, while dust in other jets was much colder, around -100 degrees Fahrenheit. Dr. Kerry Lissy from Johns Hopkins University Applied Physics Laboratory, who analysed the SOFIA data, proposed an explanation. The temperature variations suggest we're seeing material from different depths within the nucleus. The warmer dust comes from near-surface layers that have been heated by the sun. The colder dust comes from deeper regions that are still thermally insulated. This temperature diversity is telling us that these jets are excavating to different depths, potentially revealing material that hasn't seen sunlight in 4 billion years. Can you imagine that material that has been frozen in darkness since before Earth had continents? Before life evolved beyond single cells? Now being blasted into space and heated by our sun for the first time? It's like opening a time capsule. Except the capsule travelled across a significant fraction of the galaxy to get here. The erosion rate also tells us something crucial about the object's future. At the observed mass loss rate, 3I/Attilas cannot survive many more close passes to any star. If it were to orbit the Sun repeatedly like a short-period comet, it would completely disintegrate within a few dozen orbits, maybe a few thousand years at most. But 3I/Atlas isn't in a bound orbit. Its trajectory is hyperbolic, meaning it's going to swing past the Sun once and then head back out into interstellar space, never to return to our solar system. This was probably its first and only close encounter with a star in billions of years. The protective crust that preserved its carbon dioxide through eons of interstellar travel finally failed when it encountered our Sun's intense radiation. It's like watching a flower bloom beautiful, dramatic, but ephemeral. We happen to catch 3I/Atlas at the one moment in its 4 billion year existence, when its frozen interior was exposed and active. But the erosion and the jets tell us something else, something that has sparked intense debate in the astronomical community. The pattern of the jets, their locations on the nucleus, and the trajectory changes they cause don't look entirely random. In fact, when you map out where the jets are located and how they're affecting the comet's motion, you start to see patterns that make some researchers very uncomfortable. The trajectory analysis started innocently enough. When you track an object through the solar system, you expect its path to be governed by gravity, the sun's pull, planets tugging on it as it passes, maybe some minor course corrections from outgassing if it's a comet, standard celestial mechanics. But when researchers at the Jet Propulsion Laboratory's Center for Near-Earth Object Studies ran the orbital calculations for 3I/Atlas through November and December 2024, something didn't fit. The object was accelerating in ways that gravity alone couldn't explain. Dr. David Farnokia, who specializes in orbit determination at JPL, noticed it first. We model non-gravitational forces all the time with comets, he explained in a technical webinar in January 2025. Outgassing creates thrust, it's basic rocket physics, but the magnitude and direction of the acceleration we were measuring for 3I/Atlas required us to adjust our models repeatedly. The object was changing velocity by approximately 0.3 millimeters per second per day. That might not sound like much, but over months, it adds up to trajectory deviations of thousands of kilometers. Here's where it gets interesting. When you model outgassing acceleration, you make assumptions about where the jets are located and which direction they're pointing. For a randomly tumbling comet with jets erupting from wherever the sun happens to be heating the surface, you'd expect the acceleration to average out somewhat chaotically. The comet spins. Different areas face the sun at different times, jets fire in semi-random directions, and the net thrust wobbles around. That's not what 3I/Atlas did. The acceleration was remarkably consistent in direction, almost always pushing the object in a way that slightly increased its velocity relative to the sun. It was as if the jets were preferentially located on the side of the comet, facing backward along its direction of travel. When a jet fires from that position, it acts like a rocket engine, accelerating the object forward. Dr. Farnokia and his team calculated that to produce the observed acceleration, roughly 60% of the outgassing had to be coming from the hemisphere facing backward along the trajectory. Is that possible naturally? Yes. Comets aren't perfect spheres, and surface composition varies. Maybe that hemisphere just happened to have more carbon dioxide. Maybe the comet's rotation axis was oriented in a way that preferentially heated that region. These things can happen by chance. But the probability isn't high, especially when combined with everything else that makes 3I/Atlas unusual. Then there's the rotation data. The Lowell Observatory in Arizona conducted a photometric study measuring how the brightness of 3I/Atlas varied over time. When an irregularly shaped object rotates, it reflects different amounts of sunlight depending on which side faces you. By tracking these brightness variations, you can determine the rotation period. For 3I/Atlas, the initial measurements in October suggested a rotation period of about 4.2 hours. But by December, something had changed. The rotation period had slowed to approximately 5.1 hours. That's a 21% decrease in rotation rate over just 2 months. Dr. Audrey Thiruin, who led the Lowell observations, was careful in her interpretation. Outgassing torques can absolutely change a comet's rotation, she stated in her preliminary findings. As jets expel material, they create torque, and if that torque isn't symmetric, the rotation rate changes. What's unusual here is the magnitude of the change in such a short time frame. It implies very substantial outgassing with a significant asymmetry component. Let's think about what that means physically. To slow down a spinning object, you need to apply torque in the opposite direction of rotation. That torque comes from jets firing at angles that aren't aligned with the spin axis. The amount of torque depends on how far from the rotation axis the jets are located, how much thrust they produce, and which direction they point. To slow 3I/Atlas's rotation by 21% in 2 months requires continuous, powerful jets positioned in exactly the right places. Could that happen naturally again? Yes, it's possible, but you're stacking coincidence on top of coincidence. The carbon dioxide abundance that shouldn't exist, the jet's position to accelerate the object forward, the outgassing pattern that slows the rotation in a consistent direction. Each individual observation has a natural explanation, but together they form a pattern that makes some scientists deeply uncomfortable. Dr. Avi Loeb from Harvard University has been perhaps the most vocal about questioning whether 3I/Atlas could be artificial. You might remember him from the debate over Oumuamua, our first detected interstellar visitor, which he controversially suggested might be alien technology. With 3I/Atlas, Loeb has been more cautious, but in a December 2024 paper, he laid out what he calls anomaly stacking. Consider the probability space, Loeb wrote. An interstellar object with unprecedented carbon dioxide abundance arrives from outside our solar system. Its outgassing produces thrust that happens to accelerate it forward along its trajectory rather than randomly. The same outgassing creates torque that consistently slows its rotation. These are not impossible coincidences, but with each additional anomaly, the probability that we're seeing purely natural phenomena decreases multiplicatively. He calculated the combined probability at somewhere between 1 in 500 and 1 in 5000, depending on which assumptions you make. Those aren't impossible odds, but they're low enough to warrant serious consideration of alternative explanations. What if 3I/Atlas isn't purely natural? What if the high carbon dioxide content serves a purpose propulsion? What if the jet placement isn't random but designed? The scientific community's response has been mixed. To put it mildly, Dr. Michelle Bannister from the University of Canterbury in New Zealand, who studies outer solar system objects, offered a counterpoint in a January 2025 perspective piece. The problem with anomaly stacking, she argued, is that it assumes independence. These observations aren't independent, they're all consequences of the object's chemical composition and structure. Once you have an unusually carbon dioxide-rich comet, explosive outgassing follows naturally. Once you have explosive outgassing, trajectory changes and rotation changes follow naturally. We're not stacking separate anomalies, we're observing expected consequences of one fundamental anomaly, the high CO₂ content. Her point is well taken. The question becomes, do we need an extraordinary explanation for the high carbon dioxide? Or is a rare but natural formation environment sufficient? Different stellar systems have different chemistries. We've already discussed carbon-rich stars. Is it really so improbable that somewhere among the 200 billion stars in our galaxy, some produce carbon dioxide-dominated comets? But here's what keeps the debate alive. We have a sample size of exactly 3 confirmed interstellar objects. Oumuamua showed no outgassing and had a weird elongated shape. 2I/Borisov looked like a normal comet, very similar to solar system comets. And now 3I/Atlas, with its impossible chemistry and convenient thrust geometry, 3 objects, 3 completely different profiles. That's either telling us that interstellar objects are incredibly diverse, which could be true, or that we're seeing a mix of natural objects and something else. The truth is, with the data we have, we can't definitively answer the artificial versus natural question. What we can do is look at what other interstellar visitors have taught us and see where 3I/Atlas fits in that broader context. Our first confirmed interstellar visitor arrived on October 19th, 2017, and it broke every rule we thought we understood about objects travelling between stars. Oumuamua Hawaiian, for Scout or Messenger, was spotted by the Pan-STARRS telescope in Hawaii as it was already leaving the solar system. By the time we realised what it was, it had already made its closest approach to the Sun and was heading back out toward interstellar space at over 196,000 miles per hour. What made Oumuamua so bizarre wasn't just that it came from another star system, it was the complete absence of any comet-like activity. No coma, no tail, no detectable outgassing whatsoever. Yet as astronomers tracked its trajectory with extreme precision, they noticed something impossible to ignore. Oumuamua was accelerating away from the Sun faster than gravity alone could explain. The acceleration was tiny, about 0.00001 meters per second per day, but it was real and measurable across multiple observatories. Dr. Marco Micheli from the European Space Agency's Near-Earth Object Coordination Center led the analysis team that confirmed this non-gravitational acceleration in a June 2018 Nature paper. "We considered every possible explanation," Micheli stated. "Solar radiation pressure pushing on the object, measurement errors, even effects from Jupiter's gravity. None of them fit the data as well as cometary outgassing. But here's the problem. We saw absolutely no evidence of outgassing in any wavelength we observed. The outgassing hypothesis required that Oumuamua was venting something, probably water or carbon monoxide, but at rates so low that our telescopes couldn't detect it. Possible, but uncomfortable. The object would need to be composed of extremely volatile ices that sublimate even in the cold outer solar system, yet somehow survive the journey through interstellar space. And it would need to have the shape that explained its unusual light curve brightness variations, suggesting either an extremely elongated cigar shape or a flat pancake shape. Neither is common among solar system objects. Then, on August 30th, 2019, amateur astronomer Gennady Borisov in Crimea spotted what would become our second confirmed interstellar visitor. Unlike Oumuamua, 2I/Borisov looked exactly like what you'd expect a comet to look like. As it approached the Sun, it developed a classic coma and tail, spectroscopic observations revealed water vapor, cyanide, and carbon monoxide, a chemical cocktail virtually identical to comets born in our own solar system. The Hubble Space Telescope observed 2I/Borisov extensively during its passage through our solar system. Dr. Dennis Bodowitz from Auburn University, who analysed the Hubble data, found comfort in the mundane. Borisov was reassuringly normal, he said in a press conference in March 2020. Its dust-to-gas ratio, its outgassing rates, its coma morphology, everything matched what we see in long-period comets from the Oort cloud. If you hadn't told me it came from another star, I would have assumed it was one of ours. The carbon monoxide to water ratio in 2I/Borisov was measured at approximately 130 for every molecule of CO. There were 30 water molecules, high compared to most solar system comets, but not unprecedented. Comet Hale-Bopp had similar ratios. The carbon dioxide measurements were taken too, showing CO₂ at roughly 1/10 the abundance of water. Again, perfectly normal. 2I/Borisov was basically telling us that comet formation around other stars happens much the same way it does around our sun. So now we have 3 data points. Oumuamua dry, rocky or metallic, accelerating mysteriously with no visible outgassing. 2I/Borisov wet, icy, behaving exactly like a solar system comet. 3I/Atlas carbon dioxide dominated, outgassing violently, with chemistry that shouldn't exist according to our models. Have you noticed the pattern? Or rather, the complete lack of pattern? 3 objects. 3 entirely different profiles. If you were an alien studying Earth and your only samples were a palm tree, a polar bear, and a mushroom, you'd probably conclude that terrestrial biology is bewilderingly diverse. That's where we are with interstellar objects. A sample size of 3 tells us almost nothing about what's typical and what's anomalous out there. Dr. Amaya Morrow-Martin, whose work we mentioned earlier, studies the population statistics of interstellar objects based on detection rates and survey completeness calculations. She estimates that several interstellar objects pass through the inner solar system every year. Most go undetected because they're small, dark, or their trajectories don't happen to cross Earth's field of view at the right time. We're seeing the tip of the iceberg, she explained in a February 2024 review paper. For every interstellar object we detect, hundreds or thousands pass through unnoticed. The 3 we've found are likely not representative of the population as a whole, they're just the ones lucky enough, or visible enough, to be spotted. This raises an important question. What makes an interstellar object detectable? Brightness matters. You need to reflect enough sunlight for our telescopes to see you. Activity matters. Outgassing creates a coma that's much easier to spot than a bare nucleus. And trajectory matters. You need to pass close enough to Earth that our surveys can pick you up. Oumuamua was detected because it came unusually close to Earth, within 15 million miles. 2I/Borisov was detected because it was actively outgassing and bright. 3I/Atlas was detected for both reasons. It passed relatively close and then became spectacularly active. But what about the quiet ones, the dark ones, the carbon-dominated objects that don't outgas because they're still too cold? We'd never see them. Our sample is biased toward objects that are either very bright, very active, or very close. The actual population of interstellar objects could be completely different from what we're observing. Consider how different our understanding of solar system comets would be if we'd only ever seen 3 of them. Imagine we'd observed Halley's Comet, Hale-Bopp, and then something like Comet 67P. We'd have 3 vastly different objects with different chemistries, different activity levels, different structures. We'd be arguing about whether comets are typically rocky or icy, whether they normally have high carbon monoxide or low, whether outbursts are common or rare. It took observing thousands of comets before we understood the general patterns and could identify the genuine outliers. We don't have that luxury with interstellar visitors. We have 3, and trying to build a comprehensive theory of interstellar object properties from 3 examples is like trying to understand all of human culture by meeting 3 random people. You might get lucky and find representative samples, or you might meet a jazz musician, a Tibetan monk, and a rodeo clown, and conclude that humanity is utterly incomprehensible. That's the fundamental challenge facing astronomers trying to interpret 3I/Atlas. Is it genuinely anomalous, one of the rare, strange objects that nature occasionally produces, or is it representative of a whole class of carbon dioxide-rich comets that we simply haven't sampled adequately yet without more data points? We're essentially arguing in the dark. But there's one comparison that might shed light on where 3I/Atlas fits. We can look at the thousands of comets born in our own solar system and see if any of them share characteristics with our mysterious visitor. The hunt for solar system comets with unusual carbon dioxide signatures has been going on for decades, and the results are revealing. Out of approximately 4,000 known comets that have been studied spectroscopically, fewer than a dozen show carbon dioxide as even the second most abundant volatile. Water dominates in virtually every case. But those rare exceptions tell us something important. They show us that nature can produce CO₂-rich comets under certain conditions. Comet Schwassmann-Wachmann 1 is perhaps the most famous example. Discovered in 1927, this comet orbits entirely between Jupiter and Saturn, never getting close enough to the Sun for water ice to sublimate significantly. Yet it undergoes dramatic outbursts where its brightness increases by factors of hundreds within days. For decades, astronomers puzzled over what was driving these eruptions, if not water. The answer came in the 1990s when infrared spectroscopy revealed massive amounts of carbon monoxide and carbon dioxide. Dr. Karen Meach from the University of Hawaii studied Schwassmann-Wachmann 1 extensively using the Keck Observatory. In a 2009 paper, she calculated that carbon monoxide and carbon dioxide together comprised at least 70% of the outgassing, with water contributing less than 30%. This comet survives in its current orbit precisely because it's not water-dominated, Meach explained. Water ice would be stable at those distances from the Sun. CO and CO₂ are not. They're what make it active, despite being so far out in the cold. But even Schwassmann-Wachmann 1, our best solar system analog for the carbon-rich comet, has a CO₂ to water ratio of maybe 2:1 at most. That's impressive compared to typical comets. But it's still nowhere near the 10:1 ratio we're seeing in 3I/Atlas. And Schwassmann-Wachmann 1 formed in our solar system, in our Sun's protoplanetary disk. It didn't have to survive billions of years of interstellar travel. Then there's the case of Comet 29P/Schwassmann-Wachmann. Yes, confusingly. There's more than one comet with that name. This particular object, also known as SW1 or Object 29P, has been called the most active comet in the solar system despite orbiting between Jupiter and Saturn. It produces outbursts every few weeks, sometimes multiple outbursts per month. Studies using the Hubble Space Telescope and ground-based infrared observatories have shown that these outbursts are driven primarily by carbon monoxide and carbon dioxide, not water. Dr. Galcerid from the University of Central Florida modeled the interior structure of 29P in a 2019 study. He proposed that the comet has a layered structure with pockets of highly volatile ices CO and CO₂ trapped beneath layers of less volatile material. When pressure builds up enough, the overlying material fractures and the volatiles explode outward. Sound familiar? It's essentially the same mechanism we discussed for 3I/Atlas, just with different proportions of ices. But here's what's critical: both Schwassmann-Wachmann comets are believed to have formed in the outer solar system, possibly in the region beyond Neptune where temperatures were cold enough for carbon monoxide and carbon dioxide to condense efficiently. They represent what happens when comets form far from the Sun in the coldest regions of our protoplanetary disk. Yet even these cold formation comets don't achieve the carbon dioxide dominance we see in 3I/Atlas. What about comets from even farther out the Oort cloud, that vast spherical shell of comets surrounding our solar system at distances up to a light year from the Sun, contains trillions of comets that have been frozen in deep space for 4.6 billion years. These are arguably the closest analogues we have to interstellar objects. They formed in the outer solar system and were then ejected to enormous distances where they've remained in cold storage ever since. When Oort cloud comets fall back toward the Sun and become visible, we can study their chemistry. The results are mixed. Some, like Comet Hale-Bopp in 1997, show elevated carbon monoxide, roughly 1 CO molecule for every 10 water molecules. That's high, but still water-dominated. Comet C1996b2 Hyakutake showed similar ratios. These comets had been frozen at temperatures just a few degrees above absolute zero for billions of years, yet they retained water as their primary volatile. In 2014, the European Space Agency's Rosetta mission provided our most detailed look ever at a comet's interior composition. After orbiting Comet 67P for 2 years and even landing a probe on its surface, Rosetta's instruments measured the ratios of different ices in unprecedented detail. The results water comprised 80% of the outgassed volatiles. Carbon dioxide came in at about 7%, carbon monoxide at 5%, and various other compounds making up the rest. Dr. Katrin Altweg from the University of Bern, who led Rosetta's mass spectrometry team, published comprehensive composition data in a 2019 review. What surprised us most, she noted, was how little the composition varied across different regions of the nucleus, whether we sampled from areas in constant sunlight or permanently shadowed regions. From the neck region or the lobes, water always dominated. The comet was remarkably homogeneous in its major volatile composition. This homogeneity suggests that the formation process, at least in our solar system, produces relatively consistent results. Yes, there's variation from comet to comet, but the basic pattern holds: water first, carbon monoxide second or third, carbon dioxide trailing, methane and ammonia in smaller amounts. The temperatures and pressures in our Sun's protoplanetary disk created this hierarchy, and it apparently persisted across different formation locations and timescales. So where does that leave 3I/Atlas? If our best carbon dioxide-rich comets only achieve ratios around 2:1 and those are considered extreme outliers, what does it mean when we observe 10:1 either 3I/Atlas represents the tail end of an extreme distribution, the 1 in a million event where everything aligned just right, or it's telling us that other stellar systems can operate under fundamentally different rules than our Sun, Doctor? Edwin Bergen from the University of Michigan studies protoplanetary disk chemistry using radio telescopes. In a January 2025 commentary on 3I/Atlas, he pointed out something crucial. Our understanding of disk chemistry comes almost entirely from studying young stars similar to our Sun, what we call solar analogues. But the galaxy contains an enormous diversity of stellar types. M-dwarfs, which are cooler and dimmer, A-type stars, which are hotter and more luminous. Binary systems, where 2 stars influence disk chemistry simultaneously. We've barely scratched the surface of understanding how different stellar environments affect the ice composition of forming planetesimals. What if 3I/Atlas formed around an M-dwarf, a small, cool red star? These stars are the most common type in the galaxy, comprising about 75% of all stars. Their protoplanetary disks would be colder than our Suns at equivalent distances, potentially shifting the condensation zones for different ices. Or what if it formed in a binary system where gravitational dynamics created unusual temperature profiles in the disk? Or around a young star still surrounded by remnants of its parent molecular cloud, enriching the disk with carbon-rich material? The possibilities multiply when you remember that 3I/Atlas had 10,000 potential parent systems. Somewhere among those stars could be an environment so different from our Sun that it routinely produces carbon dioxide-dominated comets. We just haven't studied such systems closely enough to know. But regardless of where 3I/Atlas came from, its mere existence forces us to confront uncomfortable truths about our understanding of planetary system formation. We've been building models based on one example, our solar system, and assuming those models scale universally, 3I/Atlas is a cosmic wake-up call, a visitor from a place where the rules might be written differently. And that brings us to perhaps the most important question of all. What does this strange chemistry mean for the future of planetary science and our search for life beyond Earth? The implications of 3I/Atlas extend far beyond one unusual comet. What this object is really challenging is our entire framework for understanding how planetary systems form and what kinds of chemistry are possible in the universe. And that has enormous consequences for one of humanity's most profound questions: where else might life exist? Think about how we search for habitable planets. The entire strategy is built on assumptions derived from our solar system. We look for rocky planets in the habitable zone, the distance from a star where liquid water can exist on a surface. We assume that water is essential for life because that's what we know from Earth. We model planetary atmospheres using chemistry that we understand from our own planet's history. But what if we're looking for the wrong things, Doctor? Sarah Seeger from MIT, a pioneer in exoplanet atmosphere characterization, has been pushing the field to think beyond Earth-like worlds. In a 2020 paper titled Alternative Biosignature Gases, she proposed that life could potentially use different solvents than water and different chemistry than the carbon-oxygen-hydrogen-nitrogen framework we're familiar with. But even these alternative biochemistry models assume certain baseline abundances of elements. Carbon dioxide dominance, like we see in 3I/Atlas, wasn't on the table. Here's why this matters. When planets form, they're built from the same materials as comets, the leftover ice and dust from the protoplanetary disk. In our solar system, Earth received substantial water delivery from comets and asteroids during the first billion years of its existence. Current estimates suggest that comets may have contributed anywhere from 10% to 50% of Earth's water. That water created our oceans, our atmosphere's water vapor, and ultimately became the medium in which life evolved. But imagine a planet forming in a system like 3I/Atlas's parent system, where carbon dioxide dominates over water. Comets bombarding that planet would deliver 10 times more CO₂ than H2O. The planet's early atmosphere might be thick with carbon dioxide from the start. Its surface might have frozen carbon dioxide deposits, dry ice fields, instead of water ice caps. If liquid water existed at all, it might be buried deep underground while the surface remained a carbon dioxide-dominated environment. Could life arise under those conditions? We honestly don't know. Every living thing on Earth, from bacteria to blue whales, uses water as its cellular medium. Water's unique property is its ability to dissolve both polar and nonpolar compounds. Its high heat capacity, its expansion when freezing make it ideally suited for the complex chemistry of life. Carbon dioxide can exist as a liquid, but only at high pressures and within a narrow temperature range. At standard pressure, it goes directly from solid to gas. Dr. Dirk Schulze-Makuch from Washington State University, who studies extreme environments and astrobiology, examined the possibility of carbon dioxide-based biochemistry in a 2019 review. Liquid CO₂ could theoretically serve as a solvent for some chemical reactions, he wrote, but it's a poor solvent compared to water. It doesn't dissociate salts well. it has limited temperature range for remaining liquid, and it would require organisms to operate at very different pressures than Earth life. I wouldn't say it's impossible, but it would require biochemistry so alien that we'd barely recognize it as life. Yet here's the unsettling thought: if carbon dioxide-rich planetary systems exist, and 3I/Atlas suggests they do, then there might be billions of worlds out there with chemistry we've never seriously considered. Our telescopes are designed to look for water vapor signatures in exoplanet atmospheres. Our models of habitability are calibrated for water abundance. If life exists on a CO₂-dominated world, we might not even recognize the biosignatures it produces. The discovery also forces us to rethink our models of planet formation itself. The NICE model, one of our best theories for how the solar system evolved, proposes that the giant planets formed farther out and then migrated inward, scattering comets and asteroids throughout the inner solar system. This late heavy bombardment delivered volatiles to the rocky planets and potentially seeded them with organic compounds necessary for life. But the NICE model assumes a certain distribution of materials in the protoplanetary disk: water-dominated outer regions, rocky inner regions, gas giants in between. What happens in a system where carbon dioxide dominates? Do giant planets still form? Do they migrate the same way? Does the bombardment history of rocky planets look completely different, Doctor? Alessandro Morbidelli from the Côte d'Azur Observatory, one of the architects of the NICE model, addressed this in a conference presentation in February 2025. Every time we discover something like 3I/Atlas, we have to ask, how does this fit into our dynamical models? The answer is often uncomfortable. We've optimized our theories to explain one solar system, ours. When observations force us to consider radically different initial conditions, our models don't always have good answers. There's also a practical implication for space exploration. If we ever develop the capability for interstellar travel, admittedly a distant prospect, we'll need to know what resources are available in other stellar systems. Water is crucial for human survival, for fuel production, for growing food. Current space mission concepts assume that water will be available in comet reservoirs around other stars, just like it is in our Oort cloud. But what if we arrive at a system and find that its comets are primarily carbon dioxide? That changes everything about resource extraction, life support systems, and colonization strategies. NASA's Jet Propulsion Laboratory has been running preliminary studies on what they call non-terrestrial resource utilization. These studies model how future missions might extract and process materials from comets, asteroids, and moons. Dr. Jennifer Heldman, who leads some of this research, commented in an interview following the 3I/Atlas discovery. We've been assuming a certain chemical inventory based on solar system bodies. Learning that other systems might have fundamentally different compositions means we need to develop more flexible extraction technologies. You can't use the same processes to harvest water ice and dry ice. The temperatures, pressures, and storage requirements are completely different. But perhaps the most profound implication is philosophical. For all of human history, we've asked, are we alone? The discovery of thousands of exoplanets has refined that question to, how common is life in the universe? We've been building statistical models based on estimates of how many Earth-like planets exist in habitable zones around stable stars. The Drake equation, formulated in 1961, attempts to calculate the number of civilizations in our galaxy by multiplying together various probability factors. One of those factors is the fraction of planets where life actually develops. We've been treating that as a universal constant, as if the probability of life emerging is the same everywhere, determined primarily by having liquid water and the right chemistry. But 3I/Atlas hints that the right chemistry might vary dramatically from one stellar system to another. Life might be common in water-rich systems, but impossible in CO₂-rich systems. Or vice versa, maybe we've been looking in the wrong places all along. The humbling truth is that we're only beginning to grasp the true diversity of planetary environments in the galaxy. Every interstellar visitor is a messenger, carrying information about conditions we may never directly observe. And the messages aren't always what we expect to hear. Which brings us to the final, most urgent question: what do we do with this information? And what comes next in our understanding of these mysterious visitors from beyond our solar system? The race to understand 3I/8 Lace has revealed a fundamental problem by the time we detect these interstellar visitors. They're already leaving. Oumuamua was discovered as it was exiting the solar system. We missed our chance entirely. With 2I/Borisov, we had a few months of observations before it receded beyond the reach of our best telescopes. 3I/Atlas is following the same pattern. By late January 2025, it had already passed its closest approach to the Sun and was heading back toward interstellar space, fading from view as the distance increased. This is unacceptable from a scientific standpoint. Imagine if the only way you could study a new species of animal was to catch a glimpse of it running past your window at full speed. You might see its colour, maybe count its legs, but you'd never understand its behaviour, its diet, its life cycle. That's where we are with interstellar objects. We're getting snapshots when we need detailed, long-term studies. The solution, according to a growing chorus of astronomers, is to stop waiting for these objects to come to us. We need to go to them. Dr. Andreas Hein from the Initiative for Interstellar Studies has been developing mission concepts for exactly this purpose since 2018. His team's work culminated in Project Lyra, a mission architecture designed to rapidly launch a spacecraft to intercept interstellar objects while they're still in our solar system. The challenge is speed. By the time we detect an interstellar visitor and confirm its trajectory, it's typically moving at 50,000 to 100,000 miles per hour relative to the Sun. Catching up requires either launching a probe that's already on standby ready to go within days of detection, or using gravity assists from planets to slingshot a spacecraft to incredible velocities. Project Lyra studied both approaches for Oumuamua and concluded that with current technology, an intercept mission would have been possible, but only if launched within weeks of discovery, using a heavy-lift rocket and multiple gravity assists. For 3I/Atlas, the window was slightly better because it was detected earlier in its approach. In November 2024, a group of mission planners at the Johns Hopkins Applied Physics Laboratory ran simulations for an intercept trajectory. Dr. Carey Lisser, who participated in the study, calculated that a spacecraft launched in December 2024 using a Falcon Heavy rocket could have reached 3Y/8LAS by June 2025, allowing for several months of close-range observations before the comet became too faint to study effectively. But December 2024 came and went. No mission launched. The problem wasn't technical. We have the rockets. We have the spacecraft technology. The problem was political and financial. Space missions require years of planning, congressional approval, international cooperation, and funding that runs into hundreds of millions of dollars. You can't approve and execute an interstellar intercept mission in 6 weeks, no matter how groundbreaking the science would be. This frustration has led to a bold new proposal, the Interstellar Object Observatory, or IOO, proposed by a consortium of universities and space agencies in January 2025. The IOO concept envisions a network of 3 to 5 small spacecraft kept in permanent readiness in high Earth orbit. Each spacecraft would be equipped with spectrometers, cameras, and modest propulsion systems capable of achieving about 20 kilometers per second of delta V, enough to chase down most interstellar objects detected in the inner solar system. Dr. Michelle Bannister, whom we heard from earlier, is one of the project's advocates. Think of it like having ambulances stationed around a city, she explained in the proposal presentation. You don't wait until there's an emergency to build the ambulance. You have them ready so they can respond within minutes. The IOO would work the same way spacecraft ready to launch within 48 hours of detecting an interstellar object, with trajectories calculated and approved in advance as part of a standing mission profile. The estimated cost about $800 million for development and the first 5 years of operations. That's roughly equivalent to a single flagship-class planetary science mission. But the scientific return could be extraordinary. Instead of watching interstellar objects from hundreds of millions of miles away, we'd be flying alongside them, sampling their outgassing directly, measuring their surface composition with unprecedented precision, maybe even landing on them. There's also the Comet Interceptor mission, already approved by the European Space Agency and scheduled for launch in 2029. This mission will station a spacecraft at the Sun-Earth Lagrange Point 2, a gravitationally stable location about 1 million miles from Earth. There it will wait for a pristine comet from the Oort cloud or possibly an interstellar visitor. When a suitable target is detected, Comet Interceptor will break into 3 separate probes that will fly past the object from different angles, creating a 3-dimensional map of its composition and structure. Professor Geraint Jones from University College London, the lead scientist for Comet Interceptor, noted in a 2024 update, "We're not specifically hunting for interstellar objects, but we're positioned to respond to one if it appears. The spacecraft will have fuel reserves sufficient to chase targets moving significantly faster than typical solar system comets. If another 3/Atlas arrives while we're operational, we'll be ready." But even with missions in development, there's a deeper question: what will we do if we actually got close to one of these objects and discovered something truly extraordinary? What if we found not just unusual chemistry, but evidence of deliberate structure? What if spectroscopy from a distance gives us one answer, but close-up inspection reveals something completely different? This isn't idle speculation. The scientific community is actively debating protocols for handling an interstellar object that might show signs of artificiality. The International Astronomical Union established a working group in 2023, partially in response to the Oumuamua controversy, to develop guidelines for reporting and investigating potentially artificial interstellar objects. The protocols are conservative, requiring multiple independent confirmations before any claims of artificiality would be officially recognized. But the fact that such protocols exist at all shows how seriously the possibility is being taken. Dr. Ravi Kopparapu from NASA's Goddard Space Flight Center, who sits on this working group, stated in a 2024 interview, "We're scientists. We follow evidence wherever it leads. If an interstellar object shows characteristics that cannot be explained by natural processes, we have a responsibility to investigate thoroughly. But we also have a responsibility not to jump to conclusions. The standard of evidence for extraordinary claims must be appropriately high." For 3/Atlas specifically, that standard hasn't been met. Yes, the carbon dioxide abundance is unprecedented. Yes, the jet geometry is convenient. Yes, the trajectory changes are measurable. But every single observation can be explained by natural processes, even if those processes are rare or exotic. Science requires us to exhaust all natural explanations before considering artificial ones. And we haven't exhausted the natural explanations, not by a long shot. What we need is better data, more observations, higher resolution spectroscopy, direct sampling of the outgassing, surface composition analysis, internal structure mapping, all the things that only a dedicated mission could provide. Until we have that, we're left with tantalizing hints and frustrating gaps in our understanding. The story of 3I/Atlas isn't finished. As of early 2025, the object is still being tracked by several observatories, though it's fading rapidly as it moves away from the Sun. By mid-2025, it will likely be too faint for detailed study. By 2026, it will be just another point of light indistinguishable from distant asteroids. And eventually, it will leave our solar system entirely, returning to the vast emptiness between stars. But the questions it raised will remain. Why so much carbon dioxide? Where exactly did it come from? What does its chemistry tell us about planetary systems we've never seen? Is it genuinely natural? Or are we missing something crucial because we can't get close enough to truly understand it? These questions matter because 3I/Atlas won't be the last visitor. Statistical models suggest we should detect 1 to 3 interstellar objects per year with current survey capabilities. As our telescopes improve, particularly with the upcoming Vera C. Rubin Observatory, which will scan the entire visible sky every few nights starting in 2025, that detection rate will increase dramatically. We might find dozens per year, maybe hundreds. Each one will be a messenger from a distant star system, carrying information about environments we can barely imagine. Some will be ordinary, confirming what we already know. Others, like 3I/Atlas, will be extraordinary, challenging our assumptions and forcing us to expand our understanding of what's possible in the universe. The carbon dioxide mystery of 3I/Atlas is ultimately a reminder of how little we know about the galaxy we live in. For all our telescopes and spacecraft, for all our models and theories, we're still observers looking out from a single vantage point. These interstellar visitors are our only physical samples of environments beyond our solar system. They're precious, irreplaceable data points in our quest to understand the cosmic neighborhood, and the message they're delivering is clear: the universe is far stranger, far more diverse, and far more surprising than we ever imagined. We're just beginning to listen.